Good morning. After that wonderful introduction to tabla, I think my work would be a little more easier now. So what I'll be discussing today would be a beat tracking approach to rhythm description in Indian classical music. So if that sounds too general, what I would be mainly discussing are some preliminary experiments of automatic rhythmic analysis that we did with Indian classical music per se. When I say rhythm description here, what we did was mainly to describe some of the global rhythm parameters, such as to get the avartanam period or to get the subbeat structure, which actually are not particularly global rhythm descriptors in a piece. They could change through the piece, but they can be mostly taken to be constant over the entire song at least. So, and the other aim of this work is to actually see if the state of the art in rhythm description of Western music, how can it actually generalize to Indian music, and then see if there are specific challenges which we can identify when we apply those techniques to Indian music. So some of the typical applications would be typically rhythm metadata generation. We usually have the tala metadata with the piece, but then we can always verify it. And if we want to do a rhythm-based segmentation, this would be a starting point. And other MIR tasks such as phrase modeling and automatic rhythmic accompaniment, which is, I would say, something which is pretty new. I mean, it's not even close to anything being practical. Those are some of the applications which we might be actually looking at. As we know, rhythm in Indian classical music is hierarchical. As she said, we have an avat, then we have a vibhag, which actually correspond to an avartanam and different angas in Carnatic music. And beyond that, even within a vibhag, we have the matras which define it, which would mean that we have a structure at multiple different levels. And most of the approaches do not consider this. And then, so this is one approach in which we consider this structure at two different levels, at least at the cycle level and at the beat level, so to say, which is at the measuring the matras. And so as such, tala is an abstraction, and it's just a label given to a particular kind of structure. And this particular label as such is not present in the audio signal. It's just perceived. So what we see though is in audio signals are just the multi-scale periodicities at different levels that we see, and this is the aim of the work, to actually get this particular multi-scale periodicity which we see in the audio signal. And we know that Indian music doesn't have an absolute tempo which is defined, but still, as we see, we can have a perceived tempo in terms of it being slow, medium or fast, and even actually we can even quantify it, though it may not have a particular significance in the performance context. We can still quantify it, and then for purposes, I mean for our technical purposes. So I would say a basic description of rhythm would be to get the perceived tempo, a beat, and the long-term avarth level periodicity, and a subbeat structure, which is probably a nade in Carnatic music. So what our approach is to not assign a tala label to a song, but to get the inherent periodicity which we see, and to, instead of actually assigning one periodicity, we try to estimate it over a set of periodicity candidates and see which of them give us better scores, so to say, which I'll describe shortly. And so what we do here is to do an onset detection, typically, which is the starting point for most of the pulse analysis methodologies. And when we do a relative tempo estimation and a beat tracking, this is the starting point for our algorithm. Then we actually move one step ahead and say, are there any similarity between the beats in the song? And then we construct a beat similarity matrix. This is also very well known in the literature, that, and the structure in the beat similarity matrix gives us the long-term cyclical structure which is present in the song. Apart from this, to actually zoom into the matra level and then see what is the subbeat structure, we go to the subbeat level, and then we actually plot what's called the inter-onset interval histogram, which measures onset time between onsets, and then plots a histogram over the time, and then the structure in IOI histogram would actually indicate to us the subbeat structure. So this is a broad system level diagram of the entire system, wherein from the audio we have a detection function which actually is used to get the onsets, and then we use a spectrogram to from the detection function we'll do a tempo tracking and a beat tracking to get the beat locations. Then we chop off the audio signal chop off the spectrogram at those beat locations to actually calculate a beat similarity matrix. And so the beat similarity matrix is further processed along its diagonals, which indicate periodicity to and we test the hypothesis of different cycle periods using a comb filter bank. A comb filter bank essentially averages out all the periods which are a multiple of a particular value, and then it emphasizes periodicities at a particular period, and then it gives us a rank ordered set of candidates. On the other side, we have an onset detector here, and with which we plot an IOI histogram, which is the inter-onset interval histogram, which can further be used to test a hypothesis on the subbeat structure candidates, and they're rank ordered again. So some of the algorithms which can be used are for onset detection and for tempo induction and beat location tracking. We have, these are pretty state-of-the-art methodologies for Western music as such, and they have been modified a little to actually suit our needs here. So this is an example of detected onsets here. The blue lines which you see is the detection function. It's half-wave rectified, and then there's a lot of pre-processing done on that. Whereas the red stars which you see are the onsets detected on a particular song. And what you see here in the second panel here is the onset interval histogram which I was describing. When I say DF samples, it's the frame length, which is about 23.4 milliseconds here. And when we see a peak in this onset histogram, it means that there are a whole bunch of onsets whose durations actually vary by, if I see an onset at say 500, at 500 DFs, which is 500 into 23.4 milliseconds, I have a periodicity and then the count of those particular onsets. So though I have plotted it over 2500, we would just need to look at the initial few samples to get the most of the subbeat structure. So this is a tempo track, I would say, which is got from the function which we saw here, the onset detection function, and we use an autocorrelation based method to actually get the tempo, and it's weighted, so we can see tempo lines here. And since there are multiple tempos which can be perceived in a song, it shows it at different levels, and based on the weighting function which we use, we can see that we'll choose a particular tempo, which is the maximum here, and this weighting function decides what metrical level is actually chosen for tracking the beats in the particular song. So once we have the tempo track, we'll obtain a single tempo value for the song, and then this could be very easily changed to actually account for a variable tempo by doing a dynamic programming kind of a trace through the entire tempo track. So from this, once we have a tempo track, then we do a beat tracking on that using a dynamic programming approach, which actually takes a cost function of continuity, and then it actually disallows any kind of beats which are totally out of the continuous pulse which we see, and also on the onset strengths, and then it does a beat tracking, which is what was proposed by Ellis. And once we have the beats, we chop off the signal spectrogram at the beat locations, and then we compute what's called a beat similarity matrix, which is in a way take a particular beat and then see how similar it is with all the other beats of the song, and then plot it here. So in a way, each pixel here, each dot in this image actually indicates the xth beat and the yth beat, how correlated they are. So in a way, the structure along the diagonals of this particular matrix indicate the structure of the periodicity. See, we can see a line here. This is 0, which would, each beat is of course correlated with itself, and this is the other structure which we see, which clearly shows that there is some periodicity here. And we can, there's a lot which can be inferred from the beat similarity matrix, but here we just are doing the diagonal processing. So if I add up all the diagonals and then actually plot it, this is what comes out of it. We can see peaks at different values here, and then this is perhaps the strongest peak. But then we need to actually look at multiple periodicities to actually, this directly gives us a peak, but then it's not so obvious in most of the cases. So that's why what we do is to use this. This formulation, so it might look a little tricky though, but then it's just a comb filter. It just has a set of periodicity candidates, and then which you multiply with the spectrum and then add them up. It in a way picks up, if I want a periodicity of 4, it picks up the values at 4, 8, 6, 12 and 16, adds them up, and then takes an average and then gives it back to me. And for each of the periodicity candidates over P1 to whatever periodicity we are looking at. And then this is what is looking at the subbeat structure. So we'll go back to the original histogram which we saw, and we take the tempo period and then we go and then zoom into the tempo period by a factor of q. And when we are actually looking at, so if we are looking at a subbeat structure of 3, we would look at every 1/3 of tempo period and then see if there's a structure there, or it's just like that. So here I have a particular periodicity candidate hypothesis tested over different periodicities here, and P actually is the long-term cycle periodicity we are looking at, whereas Q is the subbeat structure we are looking at. I'll just play this example for you. It's a semi-classical, I would say. It's Ambiga Naninna Nambide by Purandaradasa. It's just played in a semi-classical fashion here. So it has a subbeat structure of 3. It's in Tishra actually, Tishra Nade. And so if I actually plot the beat track version of that, so it is actually, I would actually track it at half the speed, but then it's tracking it at a little lower. So that's why we see a periodicity at the subbeat structure at 3, and a long-term periodicity can be seen at multiple levels actually, 4, 8 and 12 and 16, whereas the peak is at 16 because the BSM had a peak at 16. So this is the graph we use for all our analysis, and then instead of actually saying the identified periodicity is 3, we actually calculate what's called a confidence score, which is at the periodicity we are looking at. We calculate the value of the function which we saw previously, and then subtract it by the minimum and divide it by the range. So this actually gives us, if we have the annotated periodicity present, it would give us a confidence score of 1, and if it's not present, it would vary between 1 and 0, instead of actually making it an exact value. And then instead of a recognition task, we make it a range over 0 to 1. And since we have metrical level ambiguity which is present in any rhythm description algorithms, the accuracy is computed at what's called annotated metrical level and the allowed metrical level. So to explain this, annotated metrical level is what a musician would say, this is actually Tishanade Aditala. So that's the annotated metrical level. Whereas the allowed metrical level could also be a Tishra double speed and an Aditala which is counted as 4, or an Aditala counted as 16. So all the allowed metrical levels, which are pretty much multiples of the annotated metrical level. And so this way we can actually check accuracies at the musician annotated level and all the other allowed levels, and then see if it can find it at the musician level and at the periodicity level which is present in the signal. So the data set we use for this is a small little data set which we collected and then annotated manually using 3 or 4 people in our lab. And most of the data was provided by Hema madam. Thanks for that. And I also collected a few light classical music songs which are almost semi-classical, and then we just wanted to see the performance and then compare it with them. Most of them are manually annotated, and so if the Tala metadata was available with the song, that was actually used. So this actually shows some of the results which we got. At the correct metrical level accuracy, because of errors in beat tracking, we don't see too much of a very good accuracy at all. But what is interesting would be to look at it at the allowed metrical levels, in which finding the nade of the song gave us about a 70% accuracy on Carnatic music database, whereas it was about 80% on the light classical music database. Whereas finding out the Tala cycle period itself, it was a pretty hard task for the entire signal. So one of the main reasons for that is the precise nature of the vibhags, and without actually taking care of the sub-Tala structure, so to say, at the vibhag level, if we directly go into the long structure, we may not exactly be able to find that. For example, if we take, say, Kantachapu or a tal which has a division of 2, 3, 2, 3. We would see a periodicity at 2 and at 3, but then we may not see a periodicity at 5, because if it's not accented, and the periodicities at 2 and 3 might actually overshadow the periodicity at 5, and we might get a lower score for a periodicity at 5. So since this actually looked at only kind of 2 levels of rhythmic structure, we see this kind of an ambiguity. One important thing which I learned only during this workshop was to actually even consider the vibhag level structure. And so Carnatic music, the performance was poorer because there are a lot of kala changes when the composition goes really fast, in which case the onsets detection and the beat tracking gets confused, and then that is how the performance goes poorer. And then on the odd meter talas, the performance was relatively poorer. So one thing to be noticed here is that though there is a metrical level ambiguity, it gets, in a way, nullified when we consider both the subbeat structure and the suprabeat, the long-term periodicity, in the sense of a 3 and a 16 could also be detected as 6 and a 8, and then they would actually correspond to the same thing, but they've been just tracked at multiple metrical levels. And both of them together can be used for getting the required metadata which we want. And if we want to assign Tala labels as such for use in a browser, say CompMusic browser, it needs further information, and then we need some knowledge-based processing further based on whatever we get out of this. So an immediate improvement could be in the choice of audio regions, wherein we can choose regions in which Tala is more apparent and then use those. One way of knowing that would be to check the local variance and then see if the onsets have too much of variance. If they have too much of variance, we could ignore those regions and then consider only regions which had less variance. And metrical level ambiguity, we need a better tempo weighting function, and then some semi-supervised approaches would actually reduce metrical level ambiguities. So if looking ahead, so estimation of sub-Tala structure at the vibhag level, so which would mean a sub-beat, vibhag level, and a Tala cycle hour level structure, that's a better way of approaching the problem of rhythm description, I would say. And we need to create a Teka database, which might be very useful if you want to do rhythm description and phrase modeling together. And so we'll also need to finally revisit the whole concept of beat tracking for Indian art moving music and see if it has any contextual importance as such. I have a few examples, but since we know I've played this in the workshop, so I'll not play it again. And I would like to thank Hema madam for actually giving us this data. And these are some of the references. And this lists pretty much all the new papers in beat tracking, and then we could go through it in detail. And thank you. I'll take any questions.